Welcome to the Rock and Flows lab. In this lab, we are going to do a lot of measurements related to rock properties and flow properties. This lab is going to be advised by or supervised by Dr. Lamia Google, who is going to monitor the every activity done in the lab, including homeworks, exams, habit accreditation, and she's going also to be the safety officer of the lab. I am one of the two instructors. My name is Omar El-khatib. The second instructor of the lab is going to be Kastub, and we also have a TA whose name is Ahmed. So before going into more details about what we are going to do in today's lecture, I want to say that, or I want to urge you to read the syllabus and make sure that you have revised everything in there, so that if you have any questions, you can just email me, and you'll find also my email in the syllabus. Just make sure you know what to bring to the lab, what you cannot bring to the lab, and how many times you can be absent in the lab, which is only once. You cannot be absent more than once, and you have to tell us beforehand. So just go through the syllabus to make sure you didn't miss anything important, and let's go over it also in our first lab if you have any other questions. In the next slide, I'm going to show you like what reference that we are going that's going to be or may be helpful for some of you in writing your reports or lab reports in the future. So just try to download this reference from the UYO library, and if you didn't find it, I think you can also find a hard copy in the university library or co-library, but you will find also an online soft copy. So let me know if you have any questions, and let's start. So we first start by the outline. You may need to check the syllabus and make sure you have read everything. Syllabus is very important regarding what you need to do throughout the semester, how many times you are allowed to be absent, what you can and what you cannot bring to the lab, and everything else. So please make sure you read the syllabus and ask me any question in case you had any, and email me any problems you have. Everything is uploaded to iCourses, so you can just check your course, and you will find my email in the syllabus as well. So we're going to start talking about petroleum production cycle and the experiments we're going to run in our lab. And those experiments will revolve around rock and fluid properties. So we'll have some experiments for evaluating fluid properties, some others for evaluating rock properties, and other experiments for rock fluid related properties. So we cannot, it's actually, or they are actually related to evaluating properties that connect with rock and fluid at the same time. For the petroleum production phases, we generally have like an exploration phase and a development phase. So the difference between them is that in exploration, we try to find the reservoir, and this is the job of the geophysicists and geologists. And once there is a reservoir and we believe like we have enough amount of crude oil that's going to be proliferating if produced, then we go to the second phase, which is a development phase. And here comes the role of engineers. So we start drilling wildcat wells. If we discover oil, then we start putting this reservoir on a development plan, and we start drilling more wells and producing more crude oil. So, as we said, we have exploration phase and development phase. And in the exploration phase, this is a job of geophysicists and geologists. Here we identify a reservoir location, and after we think this is a reservoir, we start evaluating the volume of this reservoir and whether it has a large amount of crude oil, which represents the quality of that reservoir. Because sometimes some reservoirs have crude oil that is spread across a long or a large area, and then the density of its presence or its quality becomes low. We actually want the same volume or the same amount of crude oil to be accumulated in a smaller place so that we can just drill a few number of wells and produce as much as we can from this crude oil. The development engineer or the development phase is the engineer's job. So here we start drilling wells, and once we think this is a good reservoir, we start also making simulations and try out different production scenarios in order to maximize the oil production from this reservoir. So what are the characteristics of a good reservoir? When we have high porosity, high permeability, high oil saturation, that means our reservoir is good. So we can, because high porosity means it has a lot of oil. High permeability means that we can actually produce as much as we can from this oil, and high oil saturation means there is less water in that reservoir and more oil. So which is also something good for from the production standpoint. And generally there are three methods to obtain any subsurface property. Those methods are geophysical methods like seismic surveys, which we use in the exploration phase, logging and core analysis, which we use during the development phase, and well testing and production data analysis also during the development phase. So in our lab, we are going to talk about rock and fluid experiments. And as you can see, those four are some fluid properties. So we're going to measure the viscosity, density, and refractive index of our fluid, the interfacial tension between fluids, and the phase behavior of those fluids, and how these fluids saturate our porous media. So those are fluid properties, and then we'll have also three experiments for rock properties, like the porosity of that rock, the permeability of that rock, the grain size of the minerals forming the rock, and then we have rock fluid properties, like they have both the rock and fluid participating in that property. So we can measure the contact angle or rootability. We can measure we will do a spontaneous evaporation experiment, resistivity experiment, and capillary pressure experiment. So in the first experiment, we'll measure three actually experiments, we'll measure the density, viscosity, and refractive index of fluids. The density, as you know, is mass over volume. The viscosity is a measure of how the layers of the fluid have a resistance between them when they move. So measuring this resistance between those layers gives us an indication of the viscosity between them and the viscosity of that liquid. And there are generally two types of viscosities, dynamic and kinematic viscosity. So in the lab, what we're going to measure is the kinematic viscosity. And there is also the refractive index, and as you know, when light moves from one phase to another, it doesn't move in a straight line, but it bends, and this bending or refraction differs between each two different phases. So we're going to measure the refractive index of several fluids with air, and those three experiments, we'll do them in one day. And we have also, in the second experiment, we are going to measure porosity of rocks. And as we know, porosity is the pore volume divided by the bulk volume. So if you have a cylinder, the outside volume of that cylinder is the bulk volume, and it's composed of grains and pores. So in order to figure out the porosity, we need to find the volume of the pores and subdivide it by the volume of the bulk, or the bulk volume of the cylinder or rock. So pore volume is bulk volume minus the volume of the grains, and porosity is volume of the pores by the volume of the bulk, or volume of the pore. If you substitute by this equation, it becomes like this. So if you have generally, like, there is a theoretical large porosity that nothing can actually, or no material can have a larger porosity, or no rock can have a larger porosity, which is 47% or 47.64%. This assumes a perfect cubical packing of grains of equal size. as you can see here. And if you go through the derivation, you will find that the porosity in this case will be 47%. And no matter what other case you study, the porosity will never be greater than this value, no matter how those spheres are packed together. For instance, if we have a cubic packing, as we said, this is the porosity we're going to get. If we have a rhombohedral, so instead of packing them perfectly on top of each other, if the packing is similar to this one or that one, then the porosity will be far less. And imagine also having other grains of different sizes and different shapes, and they're not just spherical. The porosity goes down even more and more. And what's a typical porosity in the reservoir could range from very low values up to 20% or 25%, or even sometimes higher than that. So in general, what controls porosity is the packing, how packed the grains are. Sometimes they are packed and sorted pretty well, sometimes they are not. And also the grain size can affect the porosity. If you have a mixture of grain sizes, that can also increase the or decrease the porosity. There is also a convention that generally a mix, you know, like in reservoirs, we don't have any of these ideal cases. Our cases will probably be like a lot of irregularities. So this is something you need to be wary of when you compare idealistic cases and learning some conclusions out of them. So as I said, grain shape or angularity affects porosity and makes it less in value. Grain size distribution, when you have better sorted grains, similar, that are actually good in shape and good like similar sizes, the porosity becomes higher. But however, there are also other factors that can affect porosity. One of them is rock compaction, and as you know, when my layer of rock is buried under other layers that keep depositing, then my layer starts getting compacted by the weight of the overlying rocks or layers of rock, and therefore the porosity decreases. Another factor is the rock dissolution, because sometimes we have fluids also moving through the porous media, and those fluids can etch and eat the rock, and when they do that, they also tend to increase the porosity of that rock. The last thing is fracturing, which is also due to the stresses acting upon the formation, and these stresses could cause fracturing and fissures to occur, which also increase the porosity. And we call this secondary porosity, and that rock is entitled as having a dual porosity. And here, in the second slide, there are two measurements of porosity. One of them is, the first method is just a direct method. You have a core that's dry, you measure its weight, and then you saturate it completely with water, and you measure its weight. So if you subtract this from that, you get the weight of the water inside the pores. And since we know the density of water, and you know its mass, then you can get its volume, and this is the pore volume. The volume of the water in the pores is actually the pore volume. So this is this method, and you end up, so once here they did what we said, the weight saturated minus weight dry divided by the rho of water. This is the volume of the pores, which is here. And when you subdivide this by V bulk, you end up getting the porosity. So this is the second experiment that which is the one we are gonna do in the lab, helium porosimeter, which is based on Boyle's law. So here we have two chambers. One of them has my rod, the other one is empty, and we have a closed valve. We increase the pressure in the first one, and then we open, and we know now the P2, but we don't know the volume. And then we open the valve, and then the pressure equilibrates, and a new pressure reading is read on these two gauges, as you can see here, after opening the valves. And now we have P3 instead of P2. So P3 multiplied by the volume of this chamber plus the volume of this chamber minus the volume of the grains is going to be equal to P2V2 that we had in the beginning. And plus P1 V1 also here. So generally, yeah, we are going to use these equations in order to figure out what is the volume of the grains, and from it, knowing the bulk volume, we can estimate the pore volume, as we are going to see in the next slide. So we run our experiments 3 times. First, we use column of billets that are very solid. They don't have any porosity. This is not my rock. This is just solid billets that do not have porosity. And we run the experiment in this case, and then we rerun it with our core inside instead of the billets, and then we run it a third time without anything. And from this we end up having 3 equations with 3 unknowns, as we're going to see in the next slide. So here we have those 3 equations and 3 unknowns. The unknowns will be V1, V2, and Vg, and solving the 3 equations we can get Vg. But in the lab we will give you all the equations so that you just substitute directly in order to be able to get the grain volume, and from which you can estimate, and knowing the bulk volume, you can estimate the pore volume and the porosity. Generally, using helium over other gases is advantageous because helium has smaller molecules, so it can, and it also has high diffusivity, so it can go into the very small pores that other gases may not be able to go in, and therefore it can measure all like the porosity like very accurately compared to other gases. Also, it's an inert gas, so it's not going to react with my rock sample. Permeability is the ability of the rock to transport different fluids through its porous media. There are 3 types of permeability: absolute permeability, effective permeability, and relative permeability. And what we are going to measure in the lab is absolute permeability, which is the ability of the rock to transport a fluid through its porous media. Generally, there are some conventions about the relationship between permeability and other parameters. For example, some people say that the higher the porosity, the higher the permeability, which is like a non-convention, but it's not necessarily true. Sometimes we have high porosity and low permeability. That's also possible, or vice versa. Also, the smaller the grain size, the lower the permeability, and the better the sorting of the grains, the higher the permeability. And generally, like these values of permeability in millidarcy can tell you whether this permeability is high or low. So if it's less than 10, that's a low permeability. 10 to 100, this is high. 100 to 1000 is very high. More than 1000 is very rare actually to find, but it's exceptional if found. So in order to measure the permeability, we actually use Darcy's law in order to correlate the flow rate through our core to the pressure drop across the core. By pressure drop, I mean the pressure at the entrance and outlet of the core. And this relationship has also effective permeability of the core to one fluid divided by the viscosity of this fluid, the length of the core, and A is the cross-sectional area perpendicular to the direction of fluid flow. And generally, if you apply this equation using these dimensions, you can estimate the permeability, and in meter squared, and in order to convert it to Darcy, you can use this conversion to convert it to Darcy units. If the fluid is gas, we just use absolute permeability or effective permeability to gas by mu gas. And since it's just one fluid, we just assume that the effective permeability is the same as absolute permeability. So in the end, this is the permeability of gas that we are estimating from this experiment. So the only problem with using gases is the Klinkenberg effect or slippage effect of gas. As we know, like liquids generally like when the layer of the liquid adjacent to the pore wall would probably be stationary, but for gas that's not true. And at low pressures,
the gases will not adhere to the walls of the pores and are actually going to slip. And therefore, this effect will cause an increase or overestimation of the permeability value. So when we plot the absolute permeability against the reciprocal mean pressure across the core, which is 1 over P1 plus P2 over 2, for each measurement that we do, if we plot this trend and we extend it until an x value of 0, then this is my actual permeability, absolute permeability of the rock without the slippage effect. Once we have two phases, the permeability in Darcy equation becomes effective permeability to that phase, and therefore we use two equations, two Darcy equations, one equation per each phase. And there is also, after that, there's what we call relative permeability, which is effective permeability divided by the absolute permeability that we estimated after Klinkenberg effect. And the relative permeability to oil would also be the effective permeability to oil divided by the absolute permeability. And if you plot the relative permeability curves against oil saturation, once we have 100% oil saturation and then we start injecting gas permeability goes up while oil permeability goes down. And if we start from residual oil saturation and start injecting oil permeability goes up while gas permeability goes down until you reach critical gas saturation and also here residual oil saturation. Beyond these saturations, you probably cannot inject more of the other phase. In the fourth experiment, we do grain size evaluation, and in order to do that, you get your rock, you crush it into powder, you get a sieve or sieves, each of which has a different opening diameter, and you put your sample in the top one, and you put it in a shaker that shakes them and knocks on top of them until they separate into different size clusters. So the largest on top and the smallest on the bottom most sieve. So once it is done, you can measure the weight of each sieve and figure out what the weight of each mineral group. And then you can plot the figures that we see on the right. So we have the sizes down there and we have the weight percentage on the y-axis. And when we do that, this is actually cumulative weight percent. So it's like if you say 100, that means anything smaller than 100. For 200, anything smaller than 200. And for 500, anything smaller than 500 is accounted for. And from this figure, we can actually measure two things, heterogeneity coefficient and sorting coefficient. So heterogeneity coefficient is D60 by D10. What's D60 and D10? It says like it's the diameter of grains with a cumulative mass percentage of 60%. So cumulative mass percent of 60%, you go at 60, you hit the curve, you go down, you see what is the diameter, and this is D60. You do the same at 10, you go at 10, hit the curve, go down, and figure out what is the diameter or D10, and now you have your heterogeneity coefficient. Similarly, the sorting coefficient is the square root of D75 by D25, so we calculated the same way from this figure. If the S is between 1 and 2.5, it's well sorted, 2.5 to 4.5, moderately sorted. If it's larger than that, it's poorly sorted. If you needed to get the mean diameter of the grains caught on one sieve, then 1 over this diameter is going to be half 1 over the diameter of this sieve's openings plus 1 over the diameter of the previous sieve's opening. But generally, we're not going to do that in the lab.
And from this experiment, you can also get a grain size distribution based on the weight percent. So if you take every sieve diameter and you plot the cumulative weight percent, or you plot the weight percent that you have on this sieve, so you end up having something similar to a normal distribution curve with a certain size dominating the weight percentages of all the other sizes. In the end, you can get the surface area of your sample by subdividing the sorting coefficient by the volume of the grains. And volume of the grains can be easily estimated using the density of your rock. So for sandstones, we know that the density is 2.65, for instance. And if you measure the mass of your sample and you have the density, you can get the volume of the grains. And from this equation, you can get the surface area of your sample. And also you can get the surface area of your grains using this equation, which is 6 divided by the total weight of all your sample, multiplied by the summation of each weight accumulated on a sieve by the diameter of the opening of the sieve. So when you have the summation of this for all the sieves, you multiply it by 6 over the total weight and you get the surface area of your sample. So interfacial tension is generally the force that holds the surface of particular phase together, and generally measured in force units per length units. And as you know, like if we have any particle or molecule of water in a water phase, it's actually it's facing the same attraction and repulsion forces from all over in all the directions, but those molecules at the surface or at the interface of this fluid with another fluid do not have this balancing forces, and therefore they start accumulating or attaching together, forming a film on the surface. And this film is what actually the mosquitoes use to stand on the surface of water or the interface of water and air. And this surface tension, generally there is like surface tension and interfacial tension. We generally call surface tension when we have a gas and a liquid, otherwise we call it or generally when one of the phases is gas, and otherwise we call it interfacial tension. So interfacial tension or the surface tension between gas and crude oil is generally around 34 dynes per centimeter. So we can define the surface tension as a force per unit length, or from an energy point of view, we can say it's the change in energy by the change in surface area. So in this case, we can say it's the force divided by the length, or the energy divided by the surface area. So in the Dunaway interfacial tensiometer that we're going to use in the lab, we have a ring similar to this one, and we put submerge it in under the surface of a certain fluid, and then we start pulling it out of that interface, and we start measuring the force that needed to pull the ring out of the surface. Once it releases from the surface and pops up, this is the interfacial tension or the force needed to overcome the interfacial tension or surface tension between this fluid and air. And generally, there are some correction factors that we use based on the ring that we employed in order to correct for the force measurement that we got from the tensiometer. So we will be providing you these correction factors and we'll use them in the lab as well. So wettability is generally the affinity of rock towards one fluid over the other. So when we have two fluids that are immiscible in the porous media, which fluid does the rock like more than the other? This is what we mean by wettability. And in order to quantify it, we measure the contact angle. So therefore, we end up having 4 different wettability states, or actually more than that. So we have like water wet state, the rock likes water. We have oil wet state, the rock likes oil. And let me have the pointer out. So we have water wet state, we have oil wet state, we have intermediate wet state, which is between this and that. It doesn't prefer any of the two phases over the other. And we have mixed wettability. In mixed wettability, we have parts of the formation that are water wet and other parts that are oil wet. But generally, water weight and oil, so this case is just a special case, but generally between water weight and oil weight, we have also several grades. So we have strongly water weight when the contact angle is between 0 and 30. We have weakly water weight, intermediate weight, weakly oil weight, and strongly oil weight, depending on the contact angle. So what is the contact angle? Generally, we measure the contact angle in the denser phase. So if we have water and oil, we measure it in the water phase. And here, as you can see, the contact angle is lower than 90. So we assume that, considering also that blue is brown and oil is green and brown is actually the rock grains. So the contact angle here is lower than 90, which is water weight. And you will find that water is covering a large portions of the grains. In the oil wet case, it's the opposite. Actually, oil is covering most of the grains, and once you have an area that you can use to measure the contact angle, you'll find this contact angle is actually obtuse, and therefore this is oil wet. In mixed wet, we probably find contact angles that are water wet and contact angles that are oil wet. We can find both. So based on those contact angles, we can subdivide or we can classify our rock to be either from strongly water wet to strongly oil wet. So as you see here, if you have this mineral and we have this fluid, and you can see this shape, and the contact angle measured in the denser phase is like that, it's obtuse, then we know that this mineral doesn't like this fluid. But if it's like this, that means this mineral likes this fluid. This is why it spreads as you see, and the contact angle in this case will be very low. There is an equation that relates the shape of the interface with the contact angle. So it's called the Young-Laplace equation, and in this equation, if we have a liquid here, a gas here, and solid here, then we have three components of the interfacial forces. So we have gamma between solid and gas, and we have gamma between liquid and gas, and we have gamma between solid and liquid. And if we resolve these components, it will be gamma Lg multiplied by cosine theta plus gamma SL is equal to gamma SG, which is this equation. So in the seventh experiment, we are going to measure the fluid saturation. And this experiment is done by Dean-Stark method or Sox-Slit extraction method. So in this experiment, we have toluene in a flask here above a heater that heats the toluene above its boiling point, which is 110 degrees C. And we have a rock here that's full of water and oil, or saturated with oil and water. And once we heat the toluene goes up and starts dissolving the crude oil from inside the core. And at the same time, since the toluene temperature is higher than the water boiling point, water also starts evaporating. Both of them go around the condenser, which has a stream of cold water going from below to the top. And then once it gets colder, these two phases start condensing around the core, and they start filling this volume until they reach this level. Once they reach here, they are drained by the siphon effect into a graduated cylinder here, where they actually get colder. And once they get colder, the toluene and water and crude oil, they separate with water at the bottom, toluene and crude oil at the top, and then they drip back into the heated toluene, and so on and so forth. We leave this experiment running until the water level in the graduated cylinder doesn't change anymore. That means we extracted all the water. So now we know the volume of the water that was inside the sample, and the rest would be oil, or would have been oil. So this is the idea behind this experiment. In this also flask, we put boiling chips in order to prevent the toluene from overheating, because it's a flammable material. We don't want this happening. So generally, when the toluene goes in and dissolves the oil and evaporates the water, it may also form something called azeotrope with the water. But once they get colder in the graduated cylinder, they separate again. So in order to get the volume of the pore, we know that the volume of the pore is the volume of water plus volume of oil. And volume of water, we already know that has already accumulated at the bottom of the graduated cylinder. But how do we get the volume of the oil? So in order to do that, we measure the weight, the initial weight of the core before the succinate extraction or before the Dean-Stark method, when it had both oil and water inside it. And then after the experiment, we dry the core out and we measure the weight of the dry core. Now, when we subtract this from that, we get the weight of oil and water. So once we subtract the weight of water, which is the same as the volume of water since the density of water is 1, then we have the weight of oil. But subdivided by the density of oil, we get the volume of oil. And this is how we can get also the porosity or the volume of pores. So in order to get the capillary pressure, we know that when we have tubes of different sizes, like normal tubes, we can have the water level at or the fluid level at a certain level, but when it becomes capillary, this level will probably go higher. And there are several relationships that, or several equations that describe capillary pressure, but one major one is that capillary pressure is equal to the pressure of the non-wetting phase minus the pressure of the wetting phase. The other equation is 2 sigma cosine theta over r, and generally we use this equation for cylindrical tubes like this. So sigma is the interfacial tension between the two fluids, r is the radius of the tube, and cosine and theta is the contact angle between the two fluids and the tube itself. So we can see that tiny pores have high capillary pressure because these tiny pores like the wetting fluid more than they like the non-wetting fluid, which is air. So the wetting fluid, it will be easier. For it to go into the tube, but it's going to be very difficult for air to push that fluid out. But in larger pores, it's actually the opposite. Air can easily displace the water despite the tube liking the water more. So tiny pores have higher capillary pressure. We can also establish an indirect relationship between capillary pressure and water saturation because also, as you can see here, the larger pores have higher air saturation, but the smaller pores have lower air saturation. So there is an indirect dependence between or of capillary pressure on saturation that we can also see in this curve. So when we have 100% water saturation, capillary pressure is 0, and then as the water saturation decreases and the air starts going into the pores, the capillary pressure starts increasing until air takes the water out of all the large pores, but now it can no longer remove water from the very small pores. So no matter how the capillary pressure increases, we will not be able to go beyond this saturation, water saturation, which we call irreducible water saturation. So in general, capillary pressure drives the water or displaces water from larger pores before smaller pores in a water wet system. So in our experiment, you will use this setup. We will have this funnel and we will have a glass beads or a pack of glass beads. And then we will have the water level up to the top of these glass beads. And at the same time, the water level will be the same on this side of the burette. Here we will use a third equation for the capillary pressure. We have already shown you two forms. This is the third form, which is rho g delta h. And we will use this equation to calculate the saturation at each step. So what are our steps? First, we know that the water level is at the top of the glass beads, and also it's at the same level in the burette. So what we're going to do is that we take the burette down. So once we take the burette down, the water level will start going down also in the glass beads, and the air will start going in. So we take it down by a specific delta H, and then now we know that the new delta H, what is a new delta H, and we know the capillary pressure. When we take it down, the water level will go a little bit up because some air went into the glass beads. So this air will displace the water, which will go also a little bit up in the burette. So the difference in V here is actually the water that came out or the volume of the air that came in. So this will help us estimate the saturation of water in here, which is going to be the original volume of the pores minus the volume of air that came in divided by the original volume of the pore, and we will be able to get the saturation. So in the ninth experiment is called spontaneous imbibition, and also we know that spontaneous imbibition or imbibition is the introduction of a wetting phase into the porous media to displace the non-wetting phase. So we introduce a fluid that the rock likes to displace another fluid that the rock doesn't like. We call this process imbibition. So if my rock is water wet and it's full of oil, I'm introducing water, and water will remove the oil or will displace the oil from the rock. And generally in this process, we can have two or four displacement processes that we're going to talk about in the next slide. Let's see. So AMOT test is a test that quantifies the wettability, or other than, it's another measure of wettability other than the contact angle. So, and as we said, it includes four displacement processes. Two of them are spontaneous imbibition, and two are forced displacements. And then we can get water index and oil index from these four processes. And the Ammot-Harvey index will be the water index minus the oil index, and it ranges between -1 and 1. So the water index and oil index, how do we get them? Let's imagine this is our capillary pressure curve versus water saturation curve, and this point is our initial point. So in order to, or actually let's imagine that this point is our initial point. So imagine that capillary pressure is negative at this point, and we have residual oil saturation, and the core is full of water and a little bit of oil. So when oil starts coming in, if we just take this core and put it in a beaker that's full of oil, oil will go in a small, only a small amount of oil will go in, like spontaneously, without forcing. And then we will have to, once we reach capillary pressure of 0, and the two pressures are the same, oil and water, now in order to inject more oil, we need to force that oil into the core. So this is forced displacement from here to here until we reach a certain irreducible water saturation, and then no more water will be produced. And now if we take this core and put it in a beaker of water, water will start to go into the core spontaneously until capillary pressure is 0 and the pressure of water is the same as the pressure of oil. And then we have to force the rest of the water in by forced displacement until also we reach a certain oil saturation that we cannot go beyond, and so on and so forth. So what matters in this curve is actually those 4 points: the SCW, or irreducible water saturation, the saturation of water at capillary pressure of 0 after water spontaneous imbibition, the spontaneous imbibition of oil saturation, and the residual oil saturation. Once we use those four values into these two equations, we will get the water index and the oil index, and then we can get the Ammot-Harvey index. So in the end, we can say that the rock is water wet if the Ammot-Harvey index is between 0.3 and 1, weakly water wet between 0 and 0.3, weakly oil wet between -0.3 and 0, and oil wet between -0.3 and -1. So in order to do this in the lab, we'll just do a simple experiment. In that experiment, we'll take a core Similar to this one, we will do vacuum saturation. So we'll put the core here, we will vacuum it from air, and then we will allow the oil to go into the pores to fill them. And then we will take the core and put it in a spontaneous imbibition cell that's full of surfactant solution, and then we measure the volume of crude oil that's produced with time. And since crude oil is lighter, it will go to the top of the spontaneous imbibition cell. And we monitor this production with time, so we record it like every 1 hour, every 2 hours in order to keep track of the production of oil with this surfactant. So when done, we end up with a curve like this, which is a recovery percentage versus time. So how do we get the recovery percentage? We only know the volume of oil produced, right? So the recovery is equal to the volume of oil produced divided by the total volume of oil. I know the volume of oil produced at each point in time, but how do I get the total volume of oil that was inside the core? The total volume of oil we know is going to be mass over density. So how do we get the mass of that oil? As we have repeated several times in the lab, this mass is going to be the weight of the core completely saturated with oil minus the dry weight of the core. And this way we can get the recovery versus time. So in the TANS experiment, we're going to measure the resistivity of a rock that has one or more fluids inside of it. And generally, the rock sample here will act as a resistance in an electrical circuit, as you see in this figure. And also we know that resistivity is the inverse of conductivity. So we are going to use the system that we have in the lab in order to estimate the resistivity of course full of water or partially full of water. So as you see in this equation, we have a resistivity constant in ohm meter, which is equal to the resistance at standard conditions multiplied by the cross-sectional area, so divided by the sample length. We know that rocks are generally not conductive, so they have high resistivity, but brines are conductive and have low resistivity. So, and similarly, any other liquids. Let's see what we're going to do in the experiment. So in our experiments, we are going to measure RO. RO is the resistivity of the core when it is 100% saturated with water or brine. And we also if we know this, and also we know the resistivity of water or brine without any core, then we can get what we call formation factor. And this formation factor we actually use in Archie equation to estimate the saturation from logging. This F can also be represented as A divided by phi to the power m, and phi is the porosity of your formation, and A and m are just constants related to the formation you are drilling or you are interested in evaluating the hydrocarbon percentage in. So we have two equations for that F. And in the next slide, we will show Archie equation and how to use F or RW on it. So Archie equation is SW to the power n is equal to R node by RT, or 1 over IR. IR is here. So it's actually R node over RT is equal to SW to the power n. And n is just a saturation exponent that has a range between 1.8 and 4 and is generally 2. So if we estimate RO, then we need RT. RT is you generally get it from logs for the formation that you are interested in. But in the lab, the way we will calculate it is that we will just take some of the brine out of the core and introduce some gas or air into the core, and this way we will estimate RT. So the difference between RT and R2 is that RO is the resistivity of a fully saturated core with brine, whereas RT is the resistivity of a core that's partially saturated with brine and has another phase in there. So once we use all the relationships and put them together, we can get to this form of Archie equation, which is A divided by phi to the power m multiplied by the resistivity of water divided by the resistivity of the rock that's partially saturated with brine. So in the last experiment, we are going to draw the phase behavior curve, or what sometimes we call binodal curve. So what's the binodal curve? So generally when we try to mix two liquids together, they can form a single phase, or they can form two phases with a separating line between the two phases with an interface. And this depends on three things. Depends on the temperature, depends on the composition, and depends on the pressure as well. In this experiment, we'll do it at ambient pressure or atmospheric pressure so that the pressure is constant and we don't need to worry about it. We're just going to change the composition and the temperature. So the idea is that inside this curve, we have two phases with clear interface between them. Outside this curve, we have a single phase with no interface or cloudiness in there, just clear single phase. So in order to plot this curve, we need to find several points on this curve in order to be able to plot it. So in this experiment, we will use octane and a mixture of octane and another liquid called methoxyethanol. So generally, when the two phases, as we said, are like very mesable together and they form a single phase, we don't see any cloudiness. But once they start forming like cloudy solution, as you see here, then we have entered the two-phase region. So as we said, we're going to use octane and methoxyethanol in our experiment. So here we will do two types of experiments. In the first group of experiments, we'll run the experiment at ambient condition. We'll start by 100% methoxyethanol and 0% octane, and then start adding octane droplet by droplet until we see cloudiness, and that means we enter the two-phase region. So we record the weight of the octane and convert it to a mole fraction of octane, and we have our first point. We do the same here, but we start by 100% octane and adding methoxyethanol until we cross the two-phased region and see cloudiness. Then we record the weight of methoxyethanol that we added and convert it to mole fraction, and we have our second point. For the second group of experiments, though, we start at higher temperature. So we choose three mole fractions, 0.2, 0.5, 0.8 of octane, 0.2, 0.5, and 0.8. And then we prepare those solutions and heat them up to 80 degrees C. And then we let them cool down. So once each of them crosses the line and goes into the two-phase region, we start seeing cloudiness and the interface between the two phases. So once this happens, we record the temperature at which this happened. So for the 0.2, for example, mole fraction, it will happen around 50. For the 0.5, it will happen around 60. And for the 0.8, it will happen also below 50. So we record those temperatures, and once we do that, we have the binodal curve. We have 5 points on the binodal curve. Of course, these temperatures will differ from a fluid to another, will differ from based on the pressure and everything else. So just make sure you read the syllabus, and if you need anything else, you will always be able to reach us by email. You will find our emails in the syllabus as well, whether me or Kaustub. Both of us are going to be the instructors for the course. And also, if you need anything in the office hours, just email us before you go to ERB. So that because we are also working in another lab, so that we can move early from that lab to ERB. There is also a first homework that's not gonna take you 2 minutes to finish, so make sure you finish that and submit it by next time. And there are YouTube videos that we uploaded to Wire courses for all the experiments. So make sure that before next lab, you review the videos of viscosity, density, and refractive index so that it's easier for you in the lab and so that you can finish and leave early, also because of COVID, to reduce the congestion and
crowdedness in the lab. If you have any other concern or any other request, please email us and we will respond happily. Thank you.